morning, I will have office hours starting at 9 instead of at 10, but I'll probably have to leave by 9:45. But I'll be very good on email and over Canvas, so just kind of post questions there and so forth. So also there's two other homeworks. There's a regression one. This one again is worth about 100. This is worth 100 points, and the graphs one is worth 50 points. It's due kind of very end of the semester. It's not meant to be very hard. These are going to be mainly in design for working in MATLAB. If you haven't done MATLAB before, don't worry. It's actually fairly easy very easy to use. It's just that it makes these assignments easier to do them in MATLAB. So the other thing I want to point out is, let's see, the final report is due April 13th. Okay, that's coming up soon, but the good news is you're basically done with the work for the class at that point, right? So your other classes probably have a bunch of other stuff due in this period of time. You'll be mainly done with this stuff. There'll be poster and fun stuff after that. And you probably did a lot towards the intermediate report already, so you're probably really far along in this class, so that's great. The other thing is the lectures at this point are going to be they're still going to cover some technical ideas, but there's going to be a lot more more fun content about thinking about data as opposed to here's a specific algorithm and here's how you apply it so much. So I know a lot of you have been following along in the notes or in the videos. So that's fine. I think you'll get more out of a lot of these classes by coming to class. There's more chances to see more than just skimming through the notes and doing the homework. If you want to do that, that's fine, up to you. You're going to get more out of it actually coming to class. Okay, so any questions about the schedule before we get back to the lecture? All right, so you're still waking up from break. All right. Okay, so this random projection techniques. Okay, so what is the idea? Again, we're going to have the input, our input data in this case is we're going to think of it as a point set P, which is in RD. So this is going to be and so this is going to be interesting where D is very very large, and I'll talk about how large you'll actually want this to be for it to be interesting. Okay, so this could come up in this is going to be similar to these random projection or to these PCA problems where you're really going to want to be able to think about this naturally in RD, meaning all of the coordinates are going to mean essentially are going to have the same units on them. Okay, so this could be you're looking at a discrete distribution of something, or you've taken a bunch of stock prices and you've taken a string sequence of a bunch of them, and each of them is the price at the end of the day or the difference between a pair of prices. So each of those is a coordinate in a high-dimensional space. Okay, so each data point, so each point is going to have these D coordinates, and they're all going to roughly mean the same thing. Okay, and so the goal of this so we talked about this doing this principal component analysis and with the SVD, which was doing a form of dimensionality reduction. But what that was doing is you had a set of data points, and the goal was essentially to find a subspace through here so that if I projected all of my points onto this subspace, I projected them all onto the subspace, that the sum of all these, I guess the squared lengths of these distances was not too much. I didn't I didn't have to project them very far. And so the goal, in this case again, will be to go to kind of live in some lower dimensional, k-dimensional subspace where k is going to be much less than d. If you're not used to it, if you see a less than sign, it's kind of an informal way of saying it's not just less than that value, it's a lot less than. And this is actually, this is like a semi-formal notation. People use this in papers, but it means it's going to be a lot smaller. So now this red subspace here, this is going to be so k-dimensional, where the original data lied in this high-dimensional subspace. And the smaller dimensional one for PCA or SVD allowed you to often go down to, say, 2 or 3 dimensions where you could maybe even draw these points. Right? You can start using your low-dimensional intuition of what's going on again. The random projections is going to work in a much larger regime here. Okay, I'm going to be thinking of D going to be very large, and K is going to be large too. So often you might think of D as in something like 100,000 and K is like 500. Okay? So we're not going to be able to get down to like 2 or 3 dimensions anymore using this. But once we're down to 500 instead of 100,000 or a million or something, we could then say, for instance, run PCA or something else on it, and this is not going to take as long as if you had this many dimensions instead. So we're going to get down to a lower dimensional subspace. And so what I talked about before was what we're going to come up with is some mapping that goes from RD to RK. And so I'd written something similar for this singular value decomposition problem before, but now I really mean that RK is not just a subspace of RD, it's actually going to be a k-dimensional space very, very formally. So we're going to, and the goal is that what we have is, what we're going to want is for all P1 and P2 in P, so for all pairs of points in our point set P, what we're going to want is the property that 1 minus epsilon if I look at the distance between this pair of points and I shrink it by a little bit, then this is going to be less than or equal to then the distance, and I'm again using this norm distance, so this is implicitly the Euclidean straight line distance. It's less than the distance between them if I'm projecting them. So these points I've projected using this mapping mu into this k-dimensional space, and I want this distance to be the true distance shrunk by a small amount to be smaller than this distance, and I also want that this is less than if I look at the original distance and I increase it by a small amount, then I want this to be larger than this. Okay, so I took the original distance, P1 minus P2, and I shrunk it by a small amount, I increased by a small amount, and I want the projected distance to fall in this range. So if epsilon is, say, 0.01, then this is like a 1% error. I want all distances in the new subspace to be preserved up to 1% error of the original distance. Okay, and I want this to hold for all pairs of points. So this is a different sort of guarantee than before. Before I was talking about projecting to a subspace and minimizing the cost of the sum of all these projections. It's kind of like an average error. This is now a worst case error. This needs to hold for all pairs of points. Okay?
Is it always possible to find such a mu?
Yes. Right. So the cool thing is that we're going to find, so the size of k is going to depend, so k, for most of this talk, although some cases I'll use a slightly different value, and so there's an asymptotic notation here. Okay, so k is going to be 1 over epsilon squared times log n. Okay, n, where, let's see, n is going to be the size of p. So n is the size of p. Epsilon is this error parameter. So if this is 1%, then 1 over epsilon squared is going to be pretty large. This is going to be like 10,000. Okay. This log n, this depends only on the size of the data. No, this is independent of d. Independent of what the original dimension of the space was. So let's think about, why would this even make sense to do something like this? To try and find this. So let's start, before we talk about this guarantee, which will be interesting in its own right. Let's think about, let's say we only had 2 points, but they each had like, each of the points was in a 1 million dimensional subspace, or a 1 million dimensional space. Okay, but I only had 2 points. How many dimensions do you think I would need then? Right, it's going to be even better than this bound. And I can have no error. I can have epsilon equals to 0. Yeah?
So 1 dimension?
Yeah, right. Yeah, so if you only have 2 points, there's always a one-dimensional line that goes through those points, and the distance between those points is exactly the distance along that line. Right? So if I'm in any dimension, it doesn't matter what the dimension of the points are. I can always draw a one-dimensional line, and then this will be R1. And then I can just look at the distance along this one dimension, and that's exactly the straight line distance between these two points. Okay? So in general, if n equals, well, I can always go to k equals n to n minus 1 dimensions. So I can always do it so I can pick a k-dimensional subspace with n minus, where it's n minus 1 dimensions. Again, it's independent of d. So if you think about this, yeah?
Is this related to the idea of like the VC dimensionality of? I know that's what's separating points, but it just seems like.
Yeah, so there's probably some relation, but this is pretty, it's probably pretty distant. So the VC dimension, which we won't unfortunately get into in this class, is sort of a combinatorial dimension of points, and this is kind of saying what is the dimension of the data you have here. What this is really saying, a better way of thinking about this is that if you go back to the singular value decomposition, the number of subspaces or right singular vectors and singular values that mattered depended on the rank of the data. And the rank is at most the number of data points that you have, or most n minus 1 of the data points. Right? There was 0 was implicitly in those sets, so the rank was actually n, but if I take the 0 point out, the origin out, then I get n minus 1. So this has to do with the rank of the matrix. I can preserve this exactly. That means that there was some red subspace up here that went through all of the data. Okay? But you know, often this n is going to be too big. Also, the other downside of this approach is that you would need to know all of the data ahead of time. This random projections approach, which I'll talk about, is going to be able to define a mapping mu which satisfies this, actually with some probabilistic terms, without knowing the data ahead of time. It's going to be, the definition of mu is going to be oblivious to the data. So I'm actually going to need another term here. This is going to be, the size is going to be n over delta, and this will so holds with probability 1 minus delta. Right, so I'm going to have, say, like 1% error of failure. It holds 99% of the time. And then I'm going to have another term, but it goes inside of the log. So it's not too bad. Usually the n is much bigger in this case. And inside of a log, taking product things kind of becomes addition. So this is adding like a 1 or 2 onto this thing. Okay. So this can be a random approach, but it's not going to need to see the data ahead of time. PCA was very dependent on the data. This is very dependent on the data, and when n is large, it's not really necessarily helping very much. Okay, so we're going to get this guarantee. How are we going to do this? How are we going to define this subspace? So let's start by going from RD to RK equals 1. So just do a one-dimensional subspace, and then it turns out we're just going to do this k times independently of each other. Okay, so I'm just going to go down to a one-dimensional subspace, and the idea is that I'll have these data points, and I want to get one dimension which describes this data. And so I'm going to essentially draw a line, and just like in this picture above, I'm going to project all the data onto this line. So I'm just projecting all the data onto the line, and then there, at some point, there's going to be some origin. In fact, I think this red line is going to go through the origin, but then each point is going to get a coordinate. So for instance, if this was P1, then this point here is the distance from the origin here is mu of P1, is the first coordinate here. So this is the one coordinate. I just give it a distance from 0. Now each of the points has a coordinate, and the distance between the points is just, if this was a distance of 2 and this was a distance of 4 here, then the distance between this point and this point is going to be 2, right? Right, so just use that as a coordinate. Okay, and so this is called this is called the random projection technique. So what I'm going to do here is this red line here I'm going to call UJ, or it'll be I'm going to create this with a random I'm going to create this with the random unit vector. Okay, so this is a random unit vector. And so we talked about how to create these random unit vectors before. Does anyone remember how we did this? Yeah?
Draw from a normal distribution and normalize it, it'll be our unit vector.
That's right, yeah. So what we need to do is draw from a normal distribution. And so this is, but this lies in RD, right? So what you're going to do is you're going to draw a G1. So you're going to create GJ1 through GJ2 up to GJD. Okay, and each GJI is going to come from a Each of these is going to come from a normal distribution, and a normal distribution, where you can get this using what's called the Box-Mueller transform, which takes in two, what should I call these, Z1 and Z2, where these two are going to be uniform. So you can create two uniform random variables between 0 and 1, do this Box-Mueller transform. This gives you a point from a normal distribution, and you're going to create D of these normal points from a normal distribution. This gives you a point from a D-dimensional normal distribution. Okay, and then we'll call this vector G, and then, or Gj, and then Uj is going to be Gj over the norm of Gj, just this norm of Gj, right? So I'm normalizing this Gaussian random, D-dimensional Gaussian random variable. It becomes a normalized vector in RD. That means its norm is going to be 1, and it's going to be uniform over all directions. It can point equally in any directions. Okay, and that's going to be this random vector. Okay, now how do I get, so this gives me one random vector. Now how do I get this coordinate, this coordinate, this value for P1? So now I'm going to call this point, let's call this point, let's call this Q1, and this will be end up being Q1J, so it's going to be the first or the jth coordinate of this. So Q1J this is going to be equal to just the dot product with Uj and P1. And if you remember the dot product over some L equals 1 to D is just the sum of the coordinates Uj, L times P1L. So that coordinate L goes from 1 to D. Essentially, each of these values, after I've normalized them, I take the product together with the coordinates of this, and this gives me Q1J, which is a single coordinate here. Okay, so this gives me one coordinate of my k-dimensional subspace. This goes to a one-dimensional subspace. Okay, and in order to get to k-dimensions, I just need to do this whole process independently k times. Okay, let me try and write this down. So I'm going to try and write this down in the form of an algorithm, just because it's a little confusing probably what is being reused and the order of these things. I'll try and write here. So let's see if I can make sure I get the right notation, consistent notation here. Okay, for j equals 1 to k. So I did this this was for the jth coordinate, so I'll do this for j going from 1 to k. So I'm going to let uj is going to be a so this is going to be a random d-dimensional so this will be my random d-dimensional unit vector. So and actually to get the right bounds of this projection, there's some bias when you project. So I need to scale this. So I'm going to set uj equals to d over k square root okay, so just to ensure that this is normalized, this could have been the Gaussian random variable. I'm going to rescale by square root d over k, and I'll explain why that is in a bit. Okay, so now for, so these are going to be enough to define this mapping. This is going to define mu, this mapping. Each of these defines the jth coordinate of mu. Okay, so then for each point pi in P, for each j in 1 to k, I'm going to create this projected point. Let me write this out. Q j is going to be equal to pi dot uj. So I'm going to take this dot product. This is going to be a point qj. I'll call this qij actually. And now this point, this mapping of pi is going to be a point qi, which is going to have coordinates qi1, qi2, up to qik. Right, so now this lives in Rk. Okay, so I need to define this mapping once based on these random unit vectors, and then for each of the points, I project them onto each of these dimensions, and this dot product just tells me the coordinates. That's it. And so for this point, I'm going to get, for the point pi, I'm going to get qij for the values j1 through k, and these are the coordinates of the new point. Okay, so this is, aside from dealing with the random Gaussians, which is not too hard, this is actually easier than running this SVD computation. Okay, and it's going to, if I rescale by d over k, then I'm going to get this stronger error bound. If I make k large enough, this stronger bound where all the distances are preserved approximately. Okay, and the larger k is, the better, you can think of the larger k is, the better the approximation guarantee is going to be. The smaller that epsilon is going to be. Okay? Let me just, okay, so this is the whole technique, the whole algorithm. Right? It's, again, very simple. This is, again, you can do this much faster, right? This is going to be, you're just, for every data point, you're just doing this dot product, and you're reading off the coordinates. Very simple, very fast to do. You don't have to, call a library to calculate the SVD. Okay, and so this technique and this approach is known as the so this technique and approach is called the Johnson-Lemonstrass lemma, or the Johnson-Lemonstrass transform, named after two guys. So this is kind of commonly used to analyze very, very high-dimensional data. So if you look at this, you'll probably see this technique. It's very simple what's going on. Okay, so let me just, one thing to point out, why do we need this scaling by square root d over k? Why is this needed? What happens if I don't do this? So this d over k should be pretty large. Right? So what happens if I don't do this d over k? Okay, let's go back and look at this picture here. So let's say I took two points. Let's highlight 2 points here, and I'll pick these in particular. Let's say I took these 2 points, and I projected them to here and here. Right? So I projected them onto the red line. What happened with the distance? It's smaller, yeah, it originally was here, now it's here. Okay, I picked these 2 points because they're on the other side of this red line, right? That makes it clear that it's smaller, but can the distances ever get larger? No, the distances always have to shrink. They always have to shrink. One way of seeing this is if you know that the Euclidean distance, let's think of the squared Euclidean distance, right? So, write something else here. The squared Euclidean distance between P1 and P2 is going to be the sum over the d coordinates. Right, squared here, right? I'm adding up all these terms. All these terms are positive. What happened if my random direction was actually one of the coordinate axes? It was one of the coordinate axes. That means that in the sum, I only used one of the terms in the sum. I only used the term that corresponded to the first coordinate axis. Okay, and so kind of on average, if there are d coordinates to start with, and then I'm choosing k of them, you kind of think of it, they happen to be the coordinate axes, and I'm essentially picking k out of the d terms in the square terms at random. And so to get the right expected value, I need to kind of estimate the value, I have to pump this back up. I'm shrinking it by k over d, the squared value, so I need to inflate it back up by d over k. And that was the squared value. If I take the square root of everything, then I need the square root d over k. Okay, so every time you do a projection, you're always shrinking the distances. This is also true if you're dealing with the SVD as well. Whenever I did the projection, I shrunk all the distances together. So this d over k term is to make sure that I'm unshrinking all the distances. Okay, so that's what's going on here. If you don't do this, you'll find that your distances are all too small. Okay, so let me just make a few notes to wrap up, and then we'll start this this pure feedback stuff. So when this Johnson-Liljestrauss theorem came out, this was in 1984, so it's not that old. It seems like a very important part of mathematics, that you can always reduce stuff down to roughly log n dimensions. It's only 1984. The first thing, it didn't quite do it this way. It took this k-dimensional subspace here, defined by these random projections, and then it made these all orthogonal to each other. They had to be orthogonal. There was a bunch of kind of follow-up things where they showed each of the coordinates can be done independently, and this still works fine. They don't need to be forced to be orthogonal. They tend to be orthogonal enough on average. Also, instead of this, you can have you can do something simpler with these J's. These can come from, each of these coordinates can come from -1, 0, and +1. You can have them so they are, instead of these Gaussian random variables, you can skip that step. You can skip going through the Box-Mueller transform. you can pick -1, 0, or +1 at random for each coordinate, and this still works. The nice thing is that a lot of them are zeros. You can actually make up to 2/3 of the entry is 0. And the zeros are good because when you're taking the dot product, those you just skip. You can skip all the zeros. Now you want to make even more of these zeros. And so there's been these fast Johnson-Lillis-Strauss approaches which are trying to make even more of these zeros. There's some technical issues. You can't always do that. You can't make too many of them zeros because you'll just miss entire things when you're doing this projection. But this is a much easier and faster way to do it. There's some class of these sub-Gaussian random variables that you can also apply here. Okay, the one last thing I wanted to point out is that if you're doing this for matrix approximation, what you want to think of as now your input data here, this is P, I had called it, basically this was A before, this is your input data. Now, before I had this was, the number of columns was D and the number of rows was N. But now the number, let's say the number of columns was N and the number of rows was D, because we're going to think of reducing the dimensionality again. And so the way to do this sketch is you create a sketch matrix that's going to be, this is now going to be D by K. And each of the entries here, say, is -1, 0, and +1 independently. And then this will create a sketch matrix B, which is going to be, this is going to be N by K. Okay, so if you're doing a sketch, like the frequent direction sketch, you just create this matrix full of these entries independently, and you can create the sketch. It turns out that in this setting, for this problem, you can actually make for each column, you can pick one element that's -1, +1, and the rest are going to be zeros. And this still works, but it needs a few more K to be a little bit larger. But this is nice because now, essentially, this matrix is almost all zero, so this is much faster. Okay, so this technique is going to be much less accurate than doing PCA directly, but it's going to be, you can do it much faster and much easier, and you can define this matrix ahead of time. You don't need to know your data to do it. Where the SVD, you needed to call this very data-dependent singular value decomposition instead. Okay. That's also kind of a very cool property. All right, so this was, I would say a few more things, but I'm going to stop here so we can start the peer feedback. Any questions on this before we wrap up? Okay, cool. So let's see. The groups, so let me see. All right, so how are we going to do this group? So I'm going to figure out how you guys are going to pair up. This is, so, okay, so here's the group pairing. Does everyone know what group number they're in? Does anyone not know what group number they're in?
Check the next email.
Okay, so the group numbers.
Can you go to the left a little bit? Or
Oh, let's see. Okay, so these are the group numberings. These are the pairings. So we tried to pair you up so people working on somewhat similar topics are going to be in the are going to be discussing with each other. Okay, and so how we will, I'm going to try and get you guys to self-group up, but we'll try and do it like in this way. So the first pairing will be here, the second pairing, third pairing, and so yeah. So if you need help with this, please let us know so you can turn off the video.